Are you someone who thinks space rocks are boring and predictable? Subscribe right now, because the new images NASA just released make that belief impossible to keep. 2 images dropped quietly on February 19th, and most people scrolled past them without realizing what they were looking at. No fireball, no glowing tail, just a tiny point of light floating through the black. But when scientists put these new images from the James Webb Space Telescope side by side with older frames from the Hubble Space Telescope, something felt off in a way that made people stop breathing for a second. The object was 3I, Atlas, and it looked exactly the same as it did months ago, even though it had moved much closer to the Sunday. That alone is strange. Any normal comet that dives toward the sun starts to fall apart in public. Ice heats up, gas boils out, dust gets pushed into long glowing tails by sunlight. You can watch the process even with small backyard telescopes. That's how comets behave. They don't keep secrets. They shed pieces of themselves like sweat. But 3I, Atlas, didn't change. The brightness didn't swell. No soft cloud formed around it. No tail grew. The Virtual Telescope Project released a side-by-side image comparing 3I, Atlas, with Comet Lemon, taken under the same conditions. Lemon behaved like a proper comet, wearing a long, ghostly tail like a scarf blowing in solar wind. 3I, Atlas, looked like a polished dot. Same size, same shape, same clean edges. People at NASA's Jet Propulsion Laboratory started running the numbers again, not because they thought the telescopes were wrong, but because the object was acting like the universe forgot to follow its own habits. As 3I, Atlas, passed closer to the sun, its path shifted. Not in a messy, chaotic way, in a smooth, steady way, like something gently nudged it from behind. The orbit drifted by just a few arcseconds. That sounds tiny until you stretch it across 200 million kilometers of space. Then that tiny angle becomes tens of thousands of kilometers of sideways movement. In space, when something changes course near the sun, there's usually a simple reason: gas jets. A comet heats up, vents gas, and the gas acts like a tiny rocket engine. That's the normal story. That's the story written in textbooks. The problem is, to push an object as heavy as 3I, Atlas, by that much, it would have to lose billions of tons of material. The sky should be full of glowing vapor around it. James Webb, with its sensitive infrared eyes, should see heat and gas. Hubble's spectrograph should catch the faint fingerprints of escaping material. The European Southern Observatory's instruments in Chile should pick up dust drifting away. They saw nothing. At the Harvard-Smithsonian Center for Astrophysics, Avi Loeb looked at the data and said the quiet part out loud. If the object were venting enough material to move like that, the cloud would be brighter than the full moon. And yet the images from November and February show the same clean, sharp point of light. No mist, no glow, no debris. This is where the story starts to get uncomfortable. Not because it points to aliens, but because it points to how little we actually see when we look at space. We like to think we know the rules. Comets do this, asteroids do that. Interstellar visitors follow patterns we can plug into equations. But every once in a while, something slides through the system that doesn't match the shapes we've drawn. The last time that happened in a big way was ʻOumuamua in 2017. It flew in from interstellar space, showed no tail, and still sped up as it left the Sunday. At the time, researchers at places like the Keck Observatory in Hawaii and the European Southern Observatory debated what could cause that. Some suggested unusual ice that doesn't leave visible dust. Some suggested odd shapes. Avi Loeb suggested something artificial, not because he wanted attention, but because the math didn't care what anyone felt comfortable with. Most scientists didn't like that idea, not because the numbers were wrong, but because the idea itself felt too heavy to carry. Now here we are again, only this time the object is far heavier, far brighter, and far easier to measure. 3I, Atlas, is not a pebble. Based on brightness and distance estimates refined by teams using Hubble and James Webb data, it could be nearly 1,000,000 times more massive than ʻOumuamua. A heavier object should be harder to push around. Yet this one drifts off course more strongly than lighter visitors we've seen before. People started asking quieter questions in lab hallways and video calls. If gas can't explain the push and sunlight pressure is too weak for something this massive, then what is doing the pushing? Gravitational tugs from planets don't line up with the timing, random errors don't move things smoothly. Whatever's happening, it is steady, calm, almost careful. Spectral data added another layer of discomfort. Instead of the dirty mix of ice and rock you expect from comets, the light bouncing off 3I, Atlas leaned toward a strange bluish tone that didn't fit cleanly into known comet types. James Webb didn't see the heat glow you'd expect from an object getting cooked near the sundae. The surface seemed to reflect light cleanly, without the rough, crumbly texture typical of icy bodies. Some researchers compared it to looking at a stone that doesn't chip when you expect it to crumble. Teams connected to NASA, JPL began comparing the object's path with the plane of the solar system. It was aligned almost too neatly with the flat disk where the planets orbit. Most random visitors come in at weird angles, slicing through the system like thrown knives. This one slid in close to the same path Earth and Mars and Jupiter follow. The odds of that alignment by chance are low. Not impossible. Just low enough to make people pause. And then there was the timing. During the period when 3I, Atlas, should have been easiest to observe from Earth, it passed into a position partly hidden by the sun's glare. It didn't vanish. It just slipped into the worst possible viewing angle. Astronomers at the Virtual Telescope Project and ESO complained about how hard it was to track at that moment. Bad luck, maybe. But bad luck stacked on top of bad luck starts to feel like a pattern. None of this proves anything strange by itself. Every piece of data has a possible natural explanation. Maybe the surface is coated in material that doesn't vent dust. Maybe the gas escaping is made of molecules we don't easily detect. Maybe we are watching a rare class of object we've never cataloged before. Science is full of maybe. That's how it grows. The problem is that all the maybes have to work together. Right now, they don't line up cleanly. Each explanation fixes one piece of the puzzle and breaks another. Fix the motion, and you can't explain the lack of a tail. Fix the lack of a tail, and you can't explain the motion. Fix the color, and the temperature makes no sense. Fix the temperature, and the composition doesn't fit. So 3I, Atlas keeps drifting through the solar system like a calm insult to neat categories. It doesn't behave like a comet. It doesn't look like an asteroid. It doesn't move the way a dead rock should move when it gets close to a star. And the more clearly we see it, thanks to tools like James Webb, Hubble, and data pipelines refined at NASA's Jet Propulsion Laboratory, the less comfortable the labels become. This is the quiet tension at the heart of the story. Not the idea that something is watching us, the idea that our boxes are too small. Every new image from Webb, every new spectrum from ground observatories in Chile, every orbit update from JPL tightens that tension. The object keeps doing the same calm, strange thing. No tail, no mess. Just steady motion, steady brightness, steady silence. And that silence is loud. Because in science, silence where noise is expected is not boring. It's a question mark that refuses to go away. That's where we are right now. A small, bright dot sliding through our neighborhood, not breaking any laws of physics, but leaning on them hard enough to make them creak. People like to think that when something strange shows up in space, scientists immediately jump to wild ideas. In real life, it's the opposite. The first reaction is always to assume the data is wrong. Someone miscalculated, a sensor glitched, a calibration file was outdated. So the first thing teams at NASA's Jet Propulsion Laboratory did was rerun everything. They checked the orbit fits again. They reprocessed the light curves. They compared James Webb's infrared readings with older Hubble spectrograph records and fresh data coming in from observatories in Chile run by the European Southern Observatory. The numbers didn't change. The drift was still there. The lack of a tail was still there. The color stayed strange. The brightness curve refused to behave like any normal comet anyone could remember. When this happens, science doesn't panic. It gets stubborn. Researchers start trying to break the problem. They invent natural explanations and push them until they fail. One idea, was that 3I, Atlas, might be made of a kind of ice that doesn't leave visible dust when it warms up. Some ices release gas that's hard to see. Hydrogen, for example, can be sneaky. But if hydrogen were pouring out at the rate needed to push something this massive, the pressure would still disturb the surface. The shape of the light reflection would change. The Virtual Telescope project would see fuzz around the edges. They didn't. Another idea was that maybe the object was spinning in a way that hid its jets from our line of sight. Comets sometimes vent in narrow streams. If those streams point away from Earth, you might miss the glow. But 3I, Atlas, was observed from different angles over weeks. The geometry changed. The silence didn't. Then there was the surface theory. Some scientists at the Harvard-Smithsonian Center for Astrophysics suggested that maybe the object is coated in a crust so tough that it traps gas beneath it, like a pressure cooker lid. That could explain the lack of dust. But pressure cookers don't vent gently. When they fail loudly. There were no sudden bursts, no flares, just smooth motion. The more natural explanations were stretched, the more they began to look like stories invented to protect comfort rather than to fit data. That's not an insult to the scientists doing the work. It's a human reflex. When something doesn't fit, we try to bend it until it does. At the Keck Observatory in Hawaii, astronomers focused on the way light scattered off the object's surface. Light doesn't just bounce randomly. The way it reflects can tell you if a surface is rough or smooth, icy or metallic, dusty or solid. The polarization signature coming off 3I, Atlas, looked unusually clean, not chaotic, not gritty, clean, like light reflecting off a polished surface. Polished surfaces exist in nature, but not many, not at this scale, not after crossing interstellar space for who knows how long. Some researchers pulled up old Arecibo legacy radar data, not because Arecibo ever saw 3I, Atlas, directly, but because decades of radar studies taught astronomers how small bodies usually scatter signals. The patterns didn't match what you'd expect from a loose pile of rock and ice. They looked more like something dense, cohesive, almost engineered in how evenly it reflected energy. That word, engineered, made people uncomfortable. Not because it means aliens, because it means stepping outside the safe fence of what we're used to talking about. So most teams avoided the word. They stuck to phrases like unusual morphology and anomalous reflectance, safe words, careful words, words that buy time. Meanwhile, the object kept moving. Orbit updates showed that the acceleration away from the sun was smooth, not jerky, not chaotic. If you plot the change over time, it forms a gentle curve. The kind of curve you get from a steady push. The kind of curve you don't get from random outbursts of gas. Teams at JPL compared the data to simulations of Comet jets. The shapes didn't line up. The real curve was too clean. The path of 3I, Atlas, through the solar system also raised eyebrows. Most interstellar objects arrive at steep angles, plunging in from above or below the plane of the planets. This one slid in almost flat, hugging the same thin disk where Earth and Mars and Jupiter orbit. Avi Loeb compared the odds of that alignment to throwing a dart in total darkness and hitting the bullseye. Not impossible, just unlikely enough to make you check if the dartboard was moved. When scientists don't like how something feels, they look for ways to make it boring again. One way to do that is to find precedents. Has anything like this happened before? ʻOumuamua was the obvious comparison. But ʻOumuamua was small, faint, and hard to measure. Many details were fuzzy. 3I. Atlas is brighter, heavier, easier to track. The data is cleaner. The excuses are thinner. This is where disagreements started to show in public talks and preprint papers. Some astronomers argued that we are simply seeing a rare type of natural object we've never cataloged before. Interstellar debris might include things far stranger than the comets we grew up studying. The universe is big. We've sampled almost none of it. It would be arrogant to assume we've seen every type of rock it can throw at us. Others countered that rarity doesn't explain everything. Rare still follows rules. Rare doesn't break all the patterns at once. Rare still leaves fingerprints you can match to known physics. 3I. Atlas leaves fingerprints that don't match cleanly to any drawer we've built. As this debate grew, something else started happening quietly. More telescopes joined the watch. The European Southern Observatory scheduled deeper runs. The James Webb team prioritized follow-up spectra. The Vera Rubin Observatory, with its wide field surveys, prepared to catch any faint changes in brightness as the object moved. Even Voyager 1's long-distance data, which helps map the background radiation environment of interstellar space, fed into models of what kind of conditions 3I, Atlas, might have crossed before reaching us. This wasn't panic, it was attention. The object itself did nothing dramatic. No sudden flare, no burst of debris, just steady movement, steady light, steady silence. And that steady silence started to feel like the loudest part of the story. Because in space, noise is normal. Comets hiss, asteroids tumble, dust scatters, gas glows. When something passes close to a star and does none of that, it's like watching a car drive without engine noise. The absence becomes the signal. The uncomfortable thought isn't that this thing is built. The uncomfortable thought is that our map of what natural means might be missing entire territories. Science likes maps, categories, names. They make the sky feel manageable. 3I. Atlas is moving through those maps like a finger smudging ink, not erasing the map, just showing where the paper is thin. And as it continues its quiet pass through the solar system, the question isn't getting smaller, it's getting sharper. If this object is natural, then the universe has been hiding a class of objects we've never really studied. If it isn't, then the universe has been hiding something else entirely. Either way, the story is no longer about a dot of light. It's about the limits of how we think we understand what drifts through our cosmic neighborhood. As more data came in, the conversation among astronomers started to change in tone. At first, it was about whether the object was strange. Then it became about how strange it was allowed to be before our explanations started to feel forced. When you reach that point in science, you're standing at the edge of what your models can comfortably explain. One of the most unsettling details was the way 3I, Atlas, brightened as it approached the sunday. Not just that it brightened, but how. Most comets follow a rough pattern. As they get closer to the sun, their brightness increases in a way that matches how much ice is turning into gas. The curve is messy. You can see little jumps and dips as jets turn on and off. With 3I, Atlas, the curve was smooth, too smooth. It brightened at a steady rate that didn't show the noisy behavior of boiling ice. Researchers comparing the light curves at NASA's Jet Propulsion Laboratory said it looked more like a reflective surface changing angle than a body shedding material. Then there was the color. Most comets have a dirty white glow mixed with faint reds and greens from gases like cyanogen and diatomic carbon. The light from 3I, Atlas, leaned blue, not a soft icy blue, a sharper electric blue that didn't match typical comet chemistry. James Webb's instruments, which can pick apart light in fine detail, didn't see the chemical fingerprints that should go with that color if it were coming from hot gas. The color seemed to come from the way the surface reflected sunlight, not from glowing vapor. People started to compare notes across institutions. The Harvard-Smithsonian team compared the spectral data with lab measurements of different minerals and metals. Some of the closest matches weren't icy mixtures at all, but high-temperature alloys used in spacecraft and jet engines. That doesn't mean the object is made of those alloys. It means the way it reflects light looks more like dense, refined material than like loose cosmic dirt. In nature, metals mix in messy ways. Here, the ratios looked oddly balanced. That word, balanced, came up again when scientists looked at the object's estimated composition. Comets are usually a chaotic mix. Ice here, rock there, dust everywhere. The preliminary breakdown for 3I, Atlas suggested very little water compared to what you'd expect. Drier than some deserts on Earth. That's not impossible. It's just strange for something that's supposed to behave like a comet near the Sunday. As the object passed through perihelion, the point where it was closest to the sun, another odd detail appeared. Instead of showing the classic tail streaming away from the sun, there were hints in some frames of faint structure pointing the wrong way. Dust and gas tails always point away from sunlight because solar radiation pressure pushes material outward. Seeing anything that seems to point toward the sun is like watching smoke blow into a fire. The data was faint, and not everyone agreed on what they were seeing. But the fact that the question was even being asked made people uneasy. By now, the list of small oddities was long. Each one could be waved away on its own. Together, they formed a pattern that didn't feel random. The path of 3I, Atlas, through the solar system also had an uncomfortable elegance to it. When researchers plotted its trajectory backward, it pointed toward a narrow region of the sky that radio astronomers have stared at for decades. The same general patch of sky where the famous WOW. The signal was detected in 1977. No one serious claimed this meant anything by itself. The universe is big. Lines cross by chance all the time. But coincidences pile up the same way grains of sand do. One grain is nothing. A pile gets your attention. The more cautious voices in the room pushed back. They reminded everyone that humans are pattern-making machines. We are very good at connecting dots that were never meant to be connected. The job of science is to resist that urge. The job of science is to let the data speak, even when it says boring things. But the data wasn't saying boring things. At the European Southern Observatory, analysts compared 3I, Atlas, with Comet Borisov, another interstellar visitor that passed through the solar system in 2019. Borisov behaved exactly like a comet should. It grew a tail, it shed gas, its brightness curve was messy and noisy. It was a textbook case of dirty ice falling apart under sunlight. That comparison made 3I. Atlas look even stranger. Two visitors from deep space. Two completely different behaviors. Same physics, same Sunday. Some researchers tried to calm the conversation by pointing out how little of the universe we've actually sampled. We've seen only 2 interstellar visitors up close. 2 data points are not a population. Maybe one behaved like a comet. Maybe the other is a rare, compact, heat-resistant body that doesn't shed dust easily. The universe can be weird without being intentional. That argument is fair. But it doesn't close the case. It opens a deeper one. If objects like 3I Atlas exist naturally, then our picture of what interstellar debris looks like is badly incomplete. It means there may be entire families of objects drifting between stars that don't look like comets or asteroids at all. We just haven't been seeing them because we weren't looking the right way. This is where the mood shifted from curiosity to unease. Not fear, unease. The feeling you get when you realize the map you've been using is missing whole continents. People working with data from Hubble and James Webb started to say the same thing in different ways. Whatever this is, it's not behaving like the categories we grew up with. That doesn't mean it's artificial. It means our categories are fragile. And fragility in science is not a weakness. It's a doorway. Because once you admit your categories might be wrong, you start seeing the sky differently. Not as a neat set of bins labeled comet, asteroid, debris, but as a messy flow of things shaped by histories we don't yet know how to read. 3I, Atlas, is still drifting, still silent, still reflecting light in that same clean, strange way. Every day it moves a little farther from the sun, and every day the chance to catch dramatic changes grows smaller. If it's going to shed a tail, now is when it should have done it. The fact that it didn't is the loudest data point of all. By the time the object began moving away from the sun, the window for easy explanations was closing. If 3I, Atlas, were going to behave like a normal comet, perihelion was the moment it should have lost its composure. That's when sunlight hits hardest, that's when ice boils fastest, that's when tails bloom into view like flags in a storm. But perihelion came and went, and the object stayed neat. No halo, no streaming dust, just that same compact point of light. This forced scientists to confront a deeper problem. If outgassing wasn't pushing it, then what was? Solar radiation pressure, the gentle push of sunlight itself, can move very small, very light objects. That's how concepts like solar sails work. But 3, I-Atlas is not a thin sheet of foil. It's massive. Based on brightness and distance estimates refined by teams using James Webb and ground observatories, it outweighs ʻOumuamua by orders of magnitude. Sunlight alone shouldn't be able to move it this much. At NASA's Jet Propulsion Laboratory, analysts ran the numbers again and again. They checked whether small gravitational nudges from planets could line up just right to explain the drift. The timing didn't match. The pushes were too smooth. Gravity tugs in lumps. The data showed a steady shove. So the conversation shifted to stranger corners of physics. Some plasma physicists wondered whether the object could be interacting with the solar wind in an unusual way, like a charged surface catching particles and converting that flow into thrust. Humans have played with this idea in labs. Stanford researchers have tested tiny prototypes that use electromagnetic fields to push against solar wind. But those are fragile experiments. Seeing something like that work at the scale of 3I, Atlas would be like watching a paper boat cross an ocean using only the breeze. Others propose that the surface might be made of some unknown material that reacts to sunlight by releasing momentum without releasing visible gas. That's a mouthful, but it boils down to this. Maybe there's a natural process we haven't discovered yet, a weird kind of rock that turns light into motion. No one has seen such a material, but nature has surprised us before. Superconductors in space were once unthinkable. Exotic ices exist in deep cold that we can barely recreate on Earth. Still, each new idea felt like it was patching one hole while opening 2 more. Another unsettling detail came from how steady the object's motion was. Comet jets flicker. They turn on and off as sunlight hits different parts of a spinning body. That creates wobbles in motion. The acceleration of 3I, Atlas, didn't wobble. It was smooth, as if the push was evenly spread over time. That's not how boiling ice behaves. It's how controlled systems behave. Control doesn't mean controlled by anyone right now. It could mean controlled by structure, a shape that channels forces evenly, a surface that interacts with energy in a uniform way. But again, those are words we usually reserve for engineered things, not cosmic debris. As the debate grew, people outside astronomy started paying attention. Headlines appeared, not because scientists were claiming alien probes, but because the word unexplained makes people lean in. The public wants clear answers. Science rarely offers them on schedule. Inside research groups, the tone stayed cautious. Papers use phrases like consistent with no known natural mechanism. That's the closest science comes to saying we're confused without admitting defeat. Confusion in science is productive. It's the feeling that tells you your current story is too simple. This moment felt familiar to older astronomers. They remembered when pulsars were first discovered, regular radio pulses from space ticking like clocks. At first, some jokingly called them little green men because nothing in nature was supposed to tick that precisely. The joke didn't last long. Pulsars turned out to be spinning neutron stars. The universe had built something that looked engineered simply because physics allowed extreme order to emerge naturally. That memory kept people grounded. Just because something looks controlled doesn't mean it is artificial. Nature can produce elegance that feels intentional. But that memory also came with a warning. When pulsars were found, scientists didn't pretend they were normal stars. They accepted a new category. They built new theory. They expanded their map of the universe. That's the crossroads 3I, Atlas, has brought us to. Either it belongs to a category we haven't properly named yet, or it forces us to stretch existing categories until they tear. As the object drifted farther from the sun, the chance to see dramatic changes shrank. The farther it gets, the colder it becomes. If it didn't shed mass near the sun, it's unlikely to suddenly start doing it now. That means the clean, silent behavior we've seen may be all we get. This leaves scientists with a strange task. They must explain motion without mess, thrust without exhaust, brightness without boiling. Each of those phrases sounds simple. Together, they form a puzzle that doesn't fit comfortably in any drawer we've built so far. And in the background of all this, another date started to loom. The next close alignment, when the object would be best placed for deep observation by multiple instruments at once. Teams were already lining up time on James Webb. Hubble schedules were being adjusted. The European Southern Observatory prepared coordinated observations from Chile. The Vera Rubin Observatory would add its wide-field eyes to catch any faint changes others might miss. If the object was going to reveal anything new about itself, that window would be the moment. Until then, the only honest thing scientists could say was this: we are watching something that behaves in a way we did not expect, and every clean image makes the problem sharper, not smaller. As the observation window approached, something subtle changed in how scientists talked about 3I, Atlas. Early on, the tone was curiosity mixed with routine doubt. Now, there was a careful seriousness in the way people chose words. Not alarm, not excitement, a kind of professional discomfort. The feeling you get when the data keeps agreeing with itself, even though you wish it wouldn't. At NASA's Jet Propulsion Laboratory, the orbit solutions had become boring in the worst possible way. Each update refined the same story. The object's path was stable. The acceleration away from the sun was still there. The sideways drift remained smooth. When boring results keep repeating, it means the weirdness isn't going away. Teams working with James Webb focused on heat. Heat is honest. If something is being pushed by internal activity, it should warm up. Webb's infrared sensors can spot tiny changes in temperature. They found no new hotspots, no fresh, warm plumes. The surface temperature stayed consistent with simple sunlight reflection, not with active venting. That left a quiet hole in the explanation. Where is the energy going? At the European Southern Observatory, researchers looked for dust so fine that even Hubble might miss it. Using sensitive imaging in different wavelengths, they searched for faint halos. They compared the frames to known comets at similar distances. The difference was stark. The comets wore faint fuzz even when they were barely active. 3I, Atlas, stayed sharp-edged, like a point cut out of the sky. Some scientists try to reframe the problem. Maybe we were wrong about the size. If the object were much smaller than we thought, sunlight pressure could matter more. But that fix broke the brightness data. If it were smaller, it would have to be far more reflective to look as bright as it does. That pushes you toward mirror-like surfaces, which again are rare in nature at cosmic scales. Others try to make the object bigger to make the brightness easier to explain. That broke the motion data. Bigger objects should be even harder to push around. Every tweak made one part of the story behave and another part rebel. At the Harvard Smithsonian Center for Astrophysics, Avi Loeb used a phrase that made people uneasy because it was simple. He said the data is telling us the object is not acting like debris. Debris is messy. Debris sheds pieces. Debris tumbles. At 3I. Atlas is not messy. It is clean in its motion and clean in its light. That word, clean, doesn't mean artificial, but it does mean structured. Structure can arise in nature. Crystals grow with sharp edges. Snowflakes form patterns that look designed. Planetary rings sort themselves into thin bands. Order is not proof of intelligence, but order does demand an explanation. Another group of researchers pointed out something that had been overlooked because it sounded too small to matter. The object's light curve did not show the chaotic flicker you'd expect from a tumbling rock. Many asteroids spin and wobble, causing their brightness to rise and fall in jagged rhythms. 3I. Atlas showed only gentle changes, consistent with either very slow rotation or a shape that reflects light evenly from many angles. Again, not impossible, just rare. The object also showed no sign of fragmentation. Many comets crack and shed pieces as they heat up. Even tough asteroids can spall under thermal stress when moving quickly between cold and heat. 3I, Atlas held together like a single piece. No crumbs, no trail of fragments, no sudden dimming from pieces breaking off. This started to reshape how people thought about its history. Whatever this object is, it has survived a long journey through interstellar space. It has likely been blasted by cosmic radiation for millions, maybe billions of years. It has passed near stars before. If it were fragile, it would have broken apart long ago. That survival alone suggests a kind of toughness that most loose piles of ice and rock don't have. The conversation drifted quietly toward longevity. Natural debris erodes. It loses sharp features over time. Micrometeorites sandblast surfaces. Radiation darkens materials. Yet 3I, Atlas reflects light cleanly, as if its surface has been preserved or renewed. No one claimed it was polished recently, but the idea that it arrived looking this intact after such a long journey was hard to swallow. This is where some scientists started to talk about selection effects. Maybe we only notice the tough ones. Fragile interstellar debris might be common, but it falls apart before we ever see it. What reaches us could be the survivors, the hard shells, the dense cores. If that's true, then 3I, Atlas, is not unique. It's just the first clear example we've caught. That idea helps. It keeps the universe natural, but it doesn't explain the smooth acceleration. It doesn't explain the lack of exhaust. It doesn't explain the strange reflectivity. It explains toughness, not behavior. As the weeks passed, the object kept doing the same quiet thing. No surprises, no sudden revelations. Just the same clean point of light, drifting out of the sun's neighborhood with the same smooth nudge away from the star. This created a strange tension. Everyone wanted a dramatic moment, a tail bursting into view, a jet lighting up, something that would snap the story back into a comfortable category. Instead, the universe offered silence. And in science, silence in the wrong place is noise. The upcoming coordinated observation window became a kind of emotional checkpoint. Not because anyone expected a miracle, but because it was the last best chance to catch anything new while the object was still close enough to study in detail. If nothing changed, then the story would move from what is happening to what has happened, from active mystery to cold case. For now, 3I, Atlas, keeps gliding away from the sun, carrying its quiet refusal to behave normally with it. As the date of the coordinated observations arrived, the pressure to find something new wasn't coming from drama-hungry headlines. It was coming from the quiet anxiety of scientists who knew that time in astronomy is not generous. Objects pass, windows close. If you miss the moment, you don't get to rewind the sky. Teams at NASA's Jet Propulsion Laboratory worked with observatories across the world to line up the same target at the same time. James Webb would look for heat and subtle chemical traces. Hubble would track shape and fine motion. The European Southern Observatory would add deep optical data from Chile. The Keck Observatory in Hawaii would look at how the light scattered. The idea wasn't to prove any wild theory. It was to corner the data, to give the object as little room as possible to hide behind uncertainty. When the coordinated data came in, it didn't explode with revelation. It whispered the same message in several different languages. No tail, no cloud, no sudden heat. The measurements from Webb matched the earlier ones. The surface temperature stayed where you'd expect for a simple reflective body warmed by sunlight. The spectra didn't show the chemical fingerprints of escaping gas. Hubble's fine tracking showed the same smooth drift in motion. ESO's deep imaging saw no faint halo that could rescue the outgassing story. Keck's polarization measurements stayed clean and oddly uniform. It was the agreement that made this moment heavy. When different instruments, built for different wavelengths, run by different teams in different parts of the world, all tell the same strange story, it becomes harder to argue that the story is a trick of perspective. At the Harvard-Smithsonian Center for Astrophysics, people began to talk about this case as a stress test for how science handles anomalies. Not in public press releases, in quiet internal discussions. The question wasn't whether the object was artificial. The question was how long you can keep calling something natural when every natural mechanism, fails to fit all the facts at once. There's a kind of etiquette in science about how far you can push language. You don't jump to extraordinary claims when ordinary explanations might still exist. But there's also a danger in clinging to ordinary explanations when the data keeps disagreeing with them. That's how dogma forms. Avi Loeb has warned about this before. Not because he wants to be controversial, but because history shows that anomalies ignored too long become missed discoveries. People started to look for historical echoes. When meteorites were first suggested to fall from the sky, many scientists laughed. Rocks don't fall from the sky, they said. Then people started collecting them. When continental drift was proposed, it was mocked for decades because no one could explain the mechanism. Then plate tectonics rewrote geology. The pattern is always the same. First denial, then debate. Then, if the evidence holds, expansion of what's considered normal. 3I, Atlas is now sitting in that awkward middle phase. Not denied, not accepted into any neat category either. Just floating there, forcing conversation, another quiet detail added to the unease. The object's trajectory, when projected forward, intersects the orbits of Mars, Venus, and Jupiter in a way that feels almost choreographed. Not close passes, that would be dangerous. Just neat crossings of the same orbital plane. Most interstellar visitors slice through at odd angles. This one glides along the cosmic highway, like it knows the lanes. Again, not impossible, just odd. Some analysts at JPL noted that during the period when the object should have been easiest to observe from Earth, it slipped behind the sun's glare. The geometry wasn't chosen by anyone. Orbits are orbits. But the timing felt cruel to observers. The best moment to catch detail was the worst moment for viewing. That bad luck, stacked on top of everything else, fed the sense that this object was revealing itself only on its own terms. The public narrative started to drift toward big questions. Are we alone? Are we being watched? Scientists push back on that framing, not because curiosity is wrong, but because it jumps several steps ahead of what the data actually says. The data says this object is strange. The data does not say why. That distinction matters. It's possible that 3I, Atlas, is teaching us about a new class of interstellar debris. Something dense, heat-resistant, smooth, and capable of interacting with sunlight or solar wind in ways we don't yet understand. That would be a huge discovery on its own. It would expand our understanding of what forms naturally between stars. It's also possible that the explanation will turn out to be boring in hindsight, a rare combination of surface chemistry and shape that happens to mimic controlled motion. Science has a way of turning the dramatic into the ordinary once the mechanism is found. But right now, there is no mechanism that fits all the facts. And that's the uncomfortable truth scientists are living with as 3I. Atlas drifts farther from the Sunday. Each day that passes without change locks in the strange behavior as the defining feature of this object, not a temporary phase. This is the point in the story where the universe stops giving easy hints and waits to see what we do with the ones we already have. 3I, Atlas isn't sending messages. It isn't flashing lights. It's doing something much quieter. It's behaving in a way that doesn't fit our expectations and daring us to decide whether our expectations need to change. As the object slipped farther from the sun, the feeling among observers shifted again, not toward closure, but toward a strange kind of waiting. The data had done its job. It had ruled out easy answers. What remained was interpretation, and interpretation moves slower than light. At NASA's Jet Propulsion Laboratory, some analysts began running backward simulations. They traced the path of 3I, Atlas, back through time, past the orbits of the planets, past the edge of the heliosphere, into interstellar space. The farther back they pushed the path, the fuzzier it became. Tiny uncertainties in present measurements grow into wide cones of possibility in the past. By the time you project millions of years backward, the object's origin becomes a region, not a point. Even so, the backward path pointed toward a general direction in the Milky Way that caught people's attention, not because it was special, but because it lined up with areas of dense star formation. Regions where stars are born in clusters. Regions where debris is common. If you wanted to explain 3I, Atlas, as natural, that's where you'd want it to come from. A crowded nursery where collisions and strange formations are more likely. This didn't solve anything. It just made one story easier to tell. At the same time, radio astronomers quietly checked whether anything unusual had been detected along the object's path. Not because anyone expected a signal, but because modern astronomy is good at layering data. The Arecibo Legacy Data Archive, though the dish is gone, still holds decades of sky records. SETI programs continue to scan the same regions of sky with new instruments. Nothing lined up with 3I Atlas. No repeating radio bursts. No narrowband signals that would make people sit up straighter. The silence stayed consistent. Silence cuts both ways. It weakens the idea of communication. It strengthens the idea of passive behavior. Whatever this object is, it is not obviously announcing itself. This pushed the conversation toward another uncomfortable possibility. Even if the object were artificial, it might not be meant to talk. It might be meant to endure. Machines don't have to signal to exist. Some probes humans send into space are meant to drift quietly, collecting data without broadcasting. Voyager 1 itself is now a silent messenger in many ways, still sending telemetry, but far beyond the range where any human voice could reach it. Thinking about Voyager changes how you frame interstellar objects. Voyager is small, fragile, and already starting to fail after a few decades in space. If another civilization had sent something across the galaxy, it would need to be far tougher than anything we've built. It would need to survive radiation, impacts, heat swings, and timescales that break our hardware. That kind of design would look strange to us. Clean, dense, resistant to change. That doesn't mean 3I Atlas is such a thing. It means that if something like that existed, it wouldn't look like a comet either. This is the uncomfortable overlap between imagination and data. The data does not force the idea of design, but it also does not rule out structures we don't yet understand how to classify. Inside the scientific community, there was a quiet effort to keep the conversation grounded. Researchers reminded each other that history is full of cosmic objects that looked impossible until better theory caught up. Quasars were once thought to be stars because no one could imagine something so bright so far away. Fast radio bursts were once dismissed as interference until patterns emerged. Nature likes to look artificial when we don't yet understand its tools. At the same time, there was an equally quiet recognition that some discoveries only happen when people are willing to ask questions that feel uncomfortable, not to jump to conclusions, but to widen the space of questions. The public pressure for answers grew louder as the object faded from easy view. People wanted a verdict, comet or not, rock or machine. Scientists had to repeat the least satisfying phrase in all of research. We don't know yet. That phrase is not weakness, it is honesty. As 3I Atlas continued its outward path, its brightness slowly fell, not because it was changing, but because distance dims everything. The object itself stayed stubbornly the same. No new features, no late bloom of gas. No dramatic twist to rescue old theories. What remained was a trail of data and a set of choices for the scientific community. Either find a new natural explanation that fits all the facts, or accept that our current categories are incomplete and build new ones. That work will take time, not weeks, not months, years. In the meantime, 3I Atlas becomes a kind of mirror for us, not because it reflects intelligence back at us, but because it reflects our discomfort with not knowing. It shows us how quickly we reach for stories when the sky doesn't behave the way we expect. It shows us how hard it is to sit with uncertainty without filling it with fear or fantasy. The object itself remains indifferent to all of this. It doesn't care how we classify it. It doesn't care what words we use. It is moving through space, obeying whatever rules govern its nature, and leaving us to decide whether those rules fit inside the ones we thought were complete. And that, more than any single explanation, is what makes this moment feel important. As the object moved beyond the range where fine details could be easily resolved, the story didn't end. It changed shape. What had been a live mystery became a long-term investigation. This is how many of the most important discoveries in science actually unfold. Not with one big reveal, but with years of slow work after the headline moment has passed. At NASA's Jet Propulsion Laboratory, teams archived every frame, every spectrum, every tiny update in the orbit. They treated 3I Atlas like a reference point, something future objects would be compared against. When the next interstellar visitor arrives, and there will be a next one, the first question will be simple. Does it behave like Borisov, like a normal comet? Or does it behave like Atlas, clean and strange? This comparison matters because it helps define populations. 2 data points become 3. 3 become 10. Patterns emerge only when you have enough examples to see what's normal and what's rare. Right now, we're trying to draw conclusions from almost nothing. That's not a failure of science. It's a reminder of how young interstellar astronomy really is. The Vera Rubin Observatory is about to change that. With its wide field surveys, it will catch faint, fast-moving objects more often than any telescope before it. That means we won't have to wait decades between visitors. The sky will start delivering more samples. Some will be boring. Some will be messy comets, shedding tails like we expect. And maybe, just maybe, some will look like 3I Atlas. If more objects show the same clean behavior, the case for a new natural class grows stronger. A family of dense, heat-resistant interstellar bodies that interact with sunlight or solar wind in ways we haven't fully modeled. That would be a huge update to our understanding of what drifts between stars. If 3I Atlas remains unique, the discomfort doesn't go away. Uniqueness in nature is rare. Even rare things tend to have cousins. Lone examples are either the first of a new class or the last survivor of something unusual. Neither option is simple. Researchers at the Harvard-Smithsonian Center for Astrophysics began talking about how this case might change how future data is handled. Instead of forcing new objects into old boxes right away, there's growing support for leaving some cases officially unclassified until enough evidence accumulates. That sounds bureaucratic, but it's actually philosophical. It's an admission that our categories are provisional, not sacred. There's also a quiet shift in how people talk about evidence of intelligence in the universe. For decades, the focus has been on radio signals and laser flashes, messages we might catch if someone else is trying to talk. But what if the first clear hint of other technology isn't a message at all? What if it's a thing, a structure, a relic drifting through space that was never meant to speak, only to exist? That idea makes some scientists uncomfortable because it blurs the line between astronomy and archaeology. We're used to studying natural processes. Studying artifacts, even hypothetical ones, changes the questions we ask. We stop asking, how does this form naturally, and start asking, who might have built this and why? Those questions feel dangerous because they invite stories where data should lead. So the safer position, for now, is to treat 3I Atlas as an extreme anomaly that demands new natural explanations. That's the position most researchers are publicly comfortable with. It keeps the work grounded. It avoids conclusions that outrun evidence. But in private conversations, many admit the same thing. They've never seen an object behave quite like this. Not in Hubble's long archive, not in data from the European Southern Observatory, not in the records that stretch back decades. This quiet admission doesn't make headlines. But it matters because it signals a genuine gap in understanding, not just a gap in data. As years pass, 3I Atlas will become a footnote in textbooks. Not because it was solved, but because it forced a rewrite of how interstellar objects are discussed. Future students will read about it as the moment when astronomers realize that visitors from other star systems might not all look like dirty snowballs. Some might be dense. Some might be clean. Some might move in ways that challenge simple models of debris drifting aimlessly through space. That shift in thinking is already happening. The object itself will fade into the darkness between stars, carrying its secrets with it. We won't chase it. We can't. Our fastest probes, even the ones launched from NASA and tracked by JPL, are slow on interstellar scales. Voyager 1 will never catch it. No planned mission can, whatever 3I Atlas is, it will remain what it is, far beyond our reach. What remains with us is the lesson. Not that the universe is watching, not that we've found proof of anything extraordinary, The lesson is quieter and more uncomfortable. We don't yet know what kinds of things move between stars. We've been guessing based on almost no data. 3I, Atlas, is the universe reminding us that guessing is not the same as knowing, and that reminder is not finished working on us yet. As time passed, the story of 3I, Atlas, began to split into two parallel tracks. One track stayed technical and slow, living in journals, datasets, and quiet meetings. The other track lived in public imagination, where every unknown detail becomes a blank space people want to fill. This split is not new. It happens whenever science brushes against questions bigger than instruments can answer quickly. Inside the technical track, the work became almost boring in its discipline. Researchers went back to first principles. What does it mean for an object to accelerate in space? How do we measure non-gravitational forces accurately? At NASA's Jet Propulsion Laboratory, small teams rechecked the force models used for comets, asteroids, and interstellar visitors. They built synthetic objects and simulations, gave them different surface properties, different shapes, different ways of interacting with light and plasma, and watched how they moved near a star. Most simulations fail to reproduce the smooth, steady push seen in 3I Atlas without creating a visible tail or heat signature. Some came close, but only by assuming surfaces or materials that have never been observed in natural bodies before. That's not proof of anything strange. It's proof that our library of natural materials might be incomplete. At the Harvard-Smithsonian Center for Astrophysics, researchers started combing through older survey data, looking for faint objects that might have behaved in similar ways, but were missed because nobody was looking for that pattern at the time. The idea was simple. Maybe 3I, Atlas, isn't unique. Maybe it's just the first one we notice because our tools are finally good enough to notice it. The problem is that older surveys weren't sensitive enough to track small changes in motion for faint objects. If something like 3I Atlas passed through decades ago, it could have slipped by unnoticed, labeled as noise or ignored because it didn't fit expectations. This raises a quiet but powerful point. Discovery is shaped by what you expect to see. If you only look for dirty comets, you will find dirty comets. If something clean passes by, you might not know what to do with it. The public track of the story moved faster. Online forums lit up with theories, some grounded, some wild. Scientists tried to stay out of that noise, not because curiosity is bad, but because speculation spreads faster than careful language. The danger isn't people imagining possibilities. The danger is people mistaking imagination for conclusion. This forced researchers to become communicators as well as analysts. They had to explain uncertainty without feeding fear or fantasy. That's hard. Humans don't like open-ended stories. We want a verdict. We want to know what the thing is. The honest answer remained the same. We don't yet know what 3I Atlas is. That answer doesn't feel satisfying, but it is powerful. It's the answer that leaves room for learning. As the object faded beyond the reach of detailed observation, the focus shifted toward preparation for the next one. The Vera Rubin Observatory will scan the sky in a way no telescope has before, catching faint, fast-moving objects more often. That means the era of one-off mysteries may be ending. Instead of 2 interstellar visitors in a decade, we may soon see several every year. When that happens, the question won't be whether objects like 3I Atlas exist. The question will be how common they are. If many new visitors behave like Borisov, shedding tails and acting like comets, then 3I Atlas becomes an odd outlier. If a significant fraction behave like Atlas, clean and silent, then the story changes. Then we are forced to rewrite what we think interstellar debris looks like. Not as fluffy snowballs, but as a mix of forms, some of them dense, some of them smooth, some of them interacting with stars in ways we don't yet model well. This future matters because it shapes how we design missions. If interstellar objects come in many forms, future probes may be built to rendezvous with them, sample them, even chase them. NASA and ESA have already talked about fast response missions that could intercept the next visitor. The designs depend on what we think we're chasing. A dirty comet requires different tools than a dense, smooth body. In that sense, 3I Atlas is already shaping the future of exploration, even if we never touch it. It's changing how scientists think about what might be out there and how quickly we need to react when something unexpected appears. The deeper lesson here isn't about this one object. It's about how science responds to discomfort. You can pretend the discomfort isn't there and keep using old models. Or you can let the discomfort reshape the models. History shows that progress comes from the second choice, even though it's slower and more painful. 3I Atlas forced that choice into the open. Not with drama, but with quiet consistency. The object didn't change its behavior to help us. It didn't give us an easy out. It simply passed through our system, did something that didn't fit neatly into our boxes, and left us to deal with the mismatch. That mismatch will linger long after the object itself is gone from view. As the immediate observations faded into archived data, the conversation around 3I Atlas turned inward, toward how we decide what counts as evidence in the first place. This is the part of science most people never see, not the telescopes or the images, but the slow arguments about standards. What level of weirdness is allowed before we admit our models are missing something important? At NASA's Jet Propulsion Laboratory, analysts began comparing 3I Atlas, not just to comets, but to everything else that experiences non-gravitational forces in space. Spacecraft, solar sails, even dust grains pushed by sunlight. The comparison wasn't meant to suggest design. It was meant to broaden the frame. Motion under force is motion under force, no matter what the object is. When you line up the curves, the push on 3I Atlas looked less like the chaotic sputter of natural jets and more like a smooth pressure profile. That doesn't answer why. It sharpens the question. At the same time, researchers at the European Southern Observatory and the Keck Observatory were building a shared library of spectra from comets, asteroids, and interstellar objects. The idea was to see whether 3I Atlas's blue-leaning reflection and clean polarization fit anywhere in the known zoo of small bodies. The match was poor, not non-existent, poor. There were hints of similarities to certain metallic asteroids and certain heat-treated materials seen in lab experiments, but nothing clean enough to point to a known natural class. This is where the idea of unknown natural processes starts to matter. Nature has a long history of doing things before we understand them. Superconductivity was observed before it was explained. Cosmic rays were detected before their sources were known. Fast radio bursts were cataloged before their origins were pinned down. In each case, the data came first. The theory limped behind. 3I Atlas might belong to that tradition, a phenomenon that shows up before we have the language for it. At the Harvard-Smithsonian Center for Astrophysics, some researchers began framing the case as a test of humility. Not humility about aliens, but humility about how narrow our view of cosmic debris has been. We built our models from the solar system outward. We assumed interstellar objects would look like things from home. That assumption may be the real bias here. Think about it this way. If you only study fish in a lake, you build a picture of what fish are. When a deep-sea creature washes up on shore, it looks impossible. Same planet, same physics. Different environment. Interstellar space is a harsher, older environment than the warm nursery of a young solar system. Objects that survive there might be nothing like the fragile comets we're used to. This reframing calmed some of the tension. It made the mystery feel less like a threat to physics and more like a reminder of how narrow our sample size has been. It also made people more patient. If 3I Atlas is part of a natural family we've never seen before, then we'll need more examples to understand it. One object is not enough to build a theory. But patience is hard when the story is public. People want meaning now. They want a label now. Scientists are trained to resist that urge, but they're still human. Even in private conversations, you could hear the pull of big questions. What if this is the first sign of technology beyond Earth? What if it's not meant to communicate, just to pass? What if we're watching something that outlived its makers? Those questions stayed mostly behind closed doors. Not because they're forbidden, but because they outrun the data. The responsible position remained the same. We have an object that doesn't fit neatly into known categories. We do not yet know why. As years pass, the data will cool. New objects will arrive. Some will behave like comets, some will behave like something else. The memory of 3I, Atlas, will fade from public attention, but it will stay alive in research circles as a case study in how anomalies are handled. There's a quiet risk here. When anomalies don't resolve quickly, they can be forgotten, filed away as curiosities. That's how discoveries get delayed. The challenge for future researchers will be to keep this case in mind when the next interstellar visitor shows up, to ask the uncomfortable questions early, to avoid forcing new data into old boxes too quickly. 3I, Atlas did not give us an answer. It gave us a problem. Problems are the raw material of science. They don't feel like progress in the moment. They feel like friction. But friction is what changes direction. The object itself will be long gone by the time the story of what it was becomes clearer. That's often how it goes in astronomy. The sky moves faster than understanding. What we're left with is not a conclusion, but a shift. A shift in how seriously we take the possibility that the universe has been throwing objects at us that we don't yet know how to name. And learning how to name things correctly is one of the quiet ways knowledge grows. As the dust settled around the first wave of debate, the case of 3I, Atlas, began to influence how new discoveries were framed. Younger researchers, especially, started pushing for language that left more room for unknown categories. Instead of forcing every new interstellar visitor into the labels of comet or asteroid, some teams began to describe them simply as interstellar objects with measured properties: shape, brightness, motion, reflection. Let the data speak before the story is chosen. This shift may sound small, but it changes how science moves. Labels guide expectations. Expectations guide what we notice. When labels are loosened, perception widens. At NASA's Jet Propulsion Laboratory, this change showed up in how orbit updates and force models were presented. Instead of assuming outgassing and then looking for evidence to support it, some analysts began presenting the non-gravitational acceleration as a fact first, with multiple possible explanations left open. This avoids baking assumptions into the model. It also makes the uncertainty visible, which is uncomfortable but honest. At the European Southern Observatory, discussions turn toward building instruments and observation plans that are sensitive to unusual behaviors. Instead of optimizing solely for tails and dust clouds, future surveys may prioritize polarization, subtle color changes, and fine motion tracking. These are the kinds of signals 3I, Atlas, made interesting. Tools evolve in response to anomalies. That's how blind spots slowly shrink. The James Webb Space Telescope team also took quiet lessons from this case. Webb is incredibly sensitive to heat and faint chemistry, but it's not optimized for tracking small, fast-moving targets over long periods. This case strengthened the argument for future space telescopes designed with rapid response capabilities, able to lock onto sudden visitors and follow them closely as they change. Hubble has done this work heroically for decades, but it was never built with interstellar archaeology in mind. There's a broader implication here. If interstellar objects can arrive with properties we don't expect, then the early warning and follow-up systems we rely on need to be flexible. We can't just prepare for what we've seen before. We have to prepare for what we haven't. This mindset echoes across other areas of astronomy. When gravitational waves were first detected, observatories had to learn to coordinate across the world in real time. When fast radio bursts were confirmed, radio telescopes had to change how they triggered alerts. New phenomena forced new habits. 3I, Atlas is quietly doing the same thing for interstellar studies. Another subtle change came in how scientists talk about evidence of intelligence beyond Earth. For decades, the search has focused on communication, radio signals, laser flashes, something meant to be noticed. Cases like 3I, Atlas raised the possibility that if there is other technology out there, it might not be sending messages at all. It might simply exist, drifting, inert, long past any purpose we would recognize. That's a harder thing to search for because it doesn't announce itself. It only becomes visible when it behaves in ways that don't fit our expectations of natural debris. This doesn't mean we should start labeling anomalies as alien. It means the space of possibilities is wider than we often admit, recognizing that width is a form of intellectual honesty, not surrender to fantasy. The long-term outcome of this case may not be a single answer. It may be a change in culture, a greater willingness to leave some boxes empty until enough data fills them naturally, a greater comfort with saying we have measured these properties, and we do not yet know the mechanism. That comfort with not knowing is fragile. It competes with the human urge to tell stories. Stories give closure. Science often withholds it. As new interstellar visitors appear in the coming years, each will be compared to 3I, Atlas. Does it shed a tail? Does it accelerate smoothly? Does it reflect light cleanly? Those questions will become routine, and slowly patterns will emerge. Some objects will cluster together in behavior, others will stand apart. Categories will form not from habit, but from evidence. This is the slow birth of understanding. Not a single moment of revelation, but a gradual reshaping of how we sort what we see. 3I. Atlas has already played its part in that reshaping. It has nudged the field to look beyond the comfortable edges of its own assumptions. And that nudge will keep echoing long after the object itself has faded into the dark. The moment that changed everything did not come with a flash or a warning. It came when the last coordinated set of observations landed and still showed nothing new. No tail, no dust, no heat plume. The same clean point of light drifting away from the sun with the same smooth push that NASA's Jet Propulsion Laboratory could measure but not explain. James Webb saw no boiling gases. Hubble's spectrograph saw no chemical trails. The European Southern Observatory's deep images showed no faint cloud hiding in the noise. The Keck Observatory's polarization data stayed clean and steady. Different instruments, different teams, different wavelengths, all agreeing on the same uncomfortable result. Whatever was moving 3I, Atlas was not behaving like any comet we've ever cataloged. At that point, the last comfortable explanation collapsed. Not because anyone wanted drama, but because the data left no room for the old story to stand on its own. Avi Loeb put it plainly in a closed discussion at the Harvard-Smithsonian Center for Astrophysics. When every standard mechanism fails at once, the problem is no longer the measurements. The problem is the model. And the model of what we think drifts between stars had just cracked. Right now, there is no verdict stamped on 3I Atlas. No one at NASA, no team at JPL, no group working with Hubble or James Webb has declared what it is. The honest position is simpler and harder to sit with. We have measured an interstellar object that does not behave like the comets and asteroids we know. It accelerates without a visible tail. It reflects light with strange consistency. It keeps its shape under heat that should have made it shed itself into space. That does not mean it is artificial. It does mean our picture of what is natural beyond our solar system is incomplete. History shows this is how science grows. Quasars once looked impossible. Pulsars once looked like clocks built by someone. In both cases, the universe turned out to be stranger than our first guesses, but still natural in ways we eventually learn to understand. 3I, Atlas, may end up in that same story. Or it may force us to add a new chapter about what survives the long, violent journey between stars. Either way, the quiet truth remains. The universe does not owe us explanations on our timeline. It reveals itself slowly, and sometimes it does so by sending us things that don't fit the boxes we already have. If you want to keep following what new data reveals about 3I, Atlas, and the next interstellar visitors that cross our path, watch the next video on your screen and subscribe so you don't miss it.